My name is Stephanie Dancer, and I'm a consultant microbiologist in a health board squash between Glasgow and Edinburgh, so really not very far away. I'm Professor of Microbiology at Edinburgh Napier, teaching biomedical students all sorts of stuff about microbiology. So it's always a little bit daunting as a clinician to be faced with such an amazing array of scientists. I do hope there's maybe one or two clinically minded folk in the audience, so that I don't have to explain everything too much, and that maybe some of you will get the gist of the view that I'm going to present to you today, because it's going to challenge you, and I don't want it to cast a shadow over the rest of the conference, but I do want to be provocative in what's going on in the clinical environment. So I've been asked to speak about how do patients actually acquire infections in hospital, and you can see from my first slide that I put the major reservoirs there. So we've got hands, which always come number one in infection prevention control, and we've got the surfaces, we've got air. I've left out water because I'm going to talk about water a bit later on, and we've got people. I'm sure you recognise the gentleman there who is examining the mannequin. You can see that he is not bare below the elbows, as we doctors have to be nowadays. I don't know when his stethoscope was last cleaned. I don't know when he last washed his hands either. But those are the main reservoirs. Let's carry on. Okay. Now, according to Weinstein, who's a very famous American professor a few years ago, 60% of acquired infection in hospitals is endogenous. What does that mean? It means that the patient actually came in with the germ that infects them in the hospital. And we have guidance for this. So 48 hours after you come into hospital, if you have an infection that is diagnosed at that point in time, that is a hospital-acquired infection. It does vary depending on what sort of infection it is. So 60% of the infections that we see were actually caused by an organism that the patient had either in their skin, their mouth, their eyes, their gut, whatever. Another 20% is attributed to the hands from staff. It doesn't have to be staff, could be the patient's own hands, visitors' hands. And finally, only 1 in 5 of the infections that we see come from the environment. Okay, I'm going to come back to that. So here's some transmission routes. So this is the tough stuff. Okay, it'll get easier as we go along. There's the direct, which is obvious. Somebody touches you and passes on an organism, which will cause an infection. That's direct contact. Then there's indirect contact. So you brush up against something, or somebody touches you with gloves, etc., etc., or there's something on a dressing which is placed on your wound. So then we have common vehicle transmission, or fomite. This is an old-fashioned term. We don't often use it nowadays in hospitals, but this basically means something's been contaminated. That's what a fomite is. Airborne, of which we've already spoken about quite a lot this morning, and I'm sure we'll be speaking about it a lot more. Airborne transmission, and finally vector-borne transmission, which are pests, and things like mosquitoes and flies and so on. So those are the main transmission routes, but things can get complicated because microorganisms are tiny. They are, as you realise, invisible to the naked eye. Sometimes we can't tell, or we don't know, or we'll never be able to find out exactly what a transmission route was for a patient. Well, we decided in our hospital to have a go and see if we could look at the transmission routes of a common pathogen called Staph aureus in my intensive care unit. And to do that, we wanted to screen patients with this particular germ because 1 in 3 patients normally carry Staph aureus, the commonest bacterial pathogen across the world. And we were going to screen staff hands because hands are the vehicle of transmission. And we also wanted to look at the surfaces, and these were hand-touch surfaces around the patient's bed, and the air. And we were going to do both passive and active air sampling. And what we were going to do was look at bioburden, so the total amount of germs, if you like, in the air and on surfaces. And we were also going to look at where Staph aureus was. We were going to genotype the Staph aureus, so to see if there was identity, so we could map out where is the Staph aureus going. Is it staff hands to the patient? Is it patients to the environment? Is it the air? So that was the reason for this particular study. And we had some standards that we were going to adhere to, so we could look at the number of hygiene passes and fails, both for surfaces, which is 5 coliform units per square centimetre. And we've also got standards for passive air sampling, which were less than 2 coliform units for a 9 centimetre agar plane. You can see that.
up on your top left there. And finally, a standard for the air, and that is less than 10 colony-forming units per cubic metre of air. So we had some standards to work with. By the way, if you do have a look at that blood agar plate up there on the left corner, it looks horrendous, doesn't it? Look at all those awful germs. My goodness me, will I die if I touch it? Can I just say that's completely normal. All the organisms on that blood agar plate are exactly what you would expect in air anywhere you go in an indoor environment. So what did we find first? The first thing we found, shock horror, is that the 5 sites which are most frequently touched around the patient's bed, the more they are touched, the more the bioburden is. So, if somebody is touching something a lot, that is where you're going to find the heaviest amount of germs. In actual fact, that's also where you're going to find the pathogens as well, because there's a relationship between heavy burden on surfaces and finding a pathogen. And we already knew that. Hand-touch equation. You see, this is why I am perhaps not quite so focused on hand hygiene as I ought to be, and my colleagues in infection control are very cross with me about this, but as far as I'm concerned, hand hygiene and cleaning the surfaces that hands touch are equally important, but all the emphasis seems to be on hand hygiene and not on the surfaces that hands touch. We're getting there. I think we're about 20 years into this now, and we're nearly there, but not quite. We're still not cleaning hospitals the way they should be cleaned. What else did we find? Well, this little graph here shows you the sampling data on the bottom, and you can see on one side of the vertical scale, we've got the average bioburden for each of the intensive care unit beds we were screening, and then on the other side, we've got the number of acquired Staph aureus infections. And there's a relationship there. And what it tells us is that as the bioburden goes up on the surfaces around the bed, so does the risk of hospital-acquired infection with the pathogen that we were using as our indicated pathogen, Staph aureus. So it's quite difficult to get this sort of data. I've only managed it once before, but it was very nice to see the relationship between the total amount of soil on surfaces, the amount of Staph aureus, and the fact that it all tied in very nicely with what was happening to patients. So we also had a look at the air, and this particular graph, I'll try and explain it, but we've got the results from passive air sampling and the results from active air sampling there. And what we did was we looked at each individual sampling, air or surface, passive sampling. Did it pass the standard, which I showed you earlier? And similarly, for the surfaces along the horizontal axis there, you can see we modelled that pass or fail with the active and the passive sampling against what we actually found on the surface. And depending on whether we use 2.5, 5, 7.5 and so on, colony forming units per square centimetre, to see where the best agreement was. And of course, what do we find? It's at 5, the magic 5. 5 colony forming units of organisms per square centimetre on a surface. It's a really nice indicator of whether your surface is risk-free or not. And this has come straight from the food industry, because funny enough, the food industry got there 20 years before we did. And that's their standard for food preparation surfaces. So, here's the genotyping study. And it's a complicated slide. Each of those boxes represents either a patient, an infected patient, or a site other than a patient down at the bottom. So the reds and yellows, you can see, are yellow is a screen-positive patient, so they had Staph aureus when they came into ICU, and the red is when we actually had an infected specimen from them. So either a tracheal aspiration or a line site or urine or whatever, or wound swab was growing an organism. And each of those arrows represent genotypic identity, not similarity. This is whole cell genomic typing. They were the same organism. So the transmission for about 60% of our transmission pairs was autologous. The patients themselves were bringing in the organism and they were getting an infection, but it was from their organism that they carried. In the nose, in the gut, under the arms, in the groin. So these are all common places to find your own particular inherent Staph aureus. And you can see at the bottom we've got a few scattered bits and pieces going on with bed tables and bed rails and medical equipment and all the rest of it.
You can see there were only 2 staff hands there that we found genotypic identity with the Staph aureus. And both of them were linked to what was going on in the air. And we've got another air, those are the blue ones, you can see the A for blue there. And we've also got another air one which was associated with a bedroll, I think. Yes, that's right. So for a whole year, looking at all the transmission pathways we could, using this indicator pathogen, we only picked up 3 from the air that had genotypic identity with other sites, and they were staff hands and a bedroll. So 2/3 of the hospital-acquired infection that we see has actually come from germs that the patient has inside them or on them. Well, I need to talk about air, and I just want to say thanks to Phil Lyson in the Netherlands, who sent me this beautiful still of somebody gently exhaling. And of course, whilst I may be a little bit concerned about how far you can go with far UV and stopping hospital-acquired infection when most patients are actually causing their own infections, I certainly think that UVC is going to have a place in the next respiratory virus pandemic if it doesn't have a place in our normal problems with norovirus and flu during the winter. The trouble is, we still need detailed specifications to prevent airborne dispersal. We need quality indoor environment air standards, which we're trying very hard to progress. You can see what I think about the open air factor as well, with the fact that I've included a little slide at the top there with the patients pushed outside on the embankment. They've all got TB. And my hospital originally was a TB hospital. We nurse patients outside in the open air. And there's something called the open air factor, which nobody seems to have managed to nail down yet, which seems as if it's extremely important in protecting people and helping people get better from respiratory ailments. This is all stuff that has never really come to the fore. All of the ventilation engineers and all the stuff done on airborne transmission of organisms was under the carpet until the pandemic came. And now you've got the focus. Now we can go forward, because air is the next medium to define. We've got foods, we've got milks, we've got waters, we've got sewage in the sea and rivers and all the rest of it, standards for all of this. But what we don't have right now are the standards we need for quality indoor air, whether it's the cinema, whether it's a healthcare environment, whether it's a school. And that's what we need. Well, I said I was going to talk about water, and you can see straight away that the only thing in water that I would worry about as a microbiologist is bacteria. And there are bacteria in a lot of the water in our environment, and also occasionally, sadly, in what we drink. And of course, who was the first person to recognise that? What a surprise. That's Florence Nightingale, an absolute star. Everything she said almost 150 years ago or more still holds true today. Fresh air. If you enclose your patient in a sealed environment, it's like roasting them in an oven, she said. I could not agree more. And I'm trying desperately for the new build of a hospital in my health board to make sure that those windows can be opened. At the moment, they said, oh, we've got a really good mechanical ventilation system, it's going to solve everything. When I think about estates and the pressures on estates for maintenance, I worry for the future. Well, have a look at this now, because if you're a UVC proponent, whatever type of UVC it may be, you think about how you can deliver UVC to the sink trap. Because this particular study, they seeded the J bend at the bottom, which you can see there, number 7 is the arrow there, with some fluorescent E. coli. So they manipulated some E. coli so that when they grow, they fluoresce green. It took 7 days for those E. coli to get up to the sink trap. And then every time somebody uses the sink, microaerosol of water containing the E. coli was spreading out from the sink. And it can spread out as much as 2 meters. If you can correct me if I'm wrong, but in my hospital, most of our sinks are actually within 2 meter range to some of the patients, and even some of the surfaces where we prepare stuff. So that's a real issue. Carry on. And this is another one, just been published from my mate Stefan Harbath in Geneva. And what they decided to do is, we know about sink traps, we know how dangerous they are. The organisms that are there are multi-drug resistant, in fact, pan-resistant, which is our terminology in clinical speak for untreatable. And they're all there down in the sinks and the plumbing in hospitals. So what they decided to do was to actually blast the sinks with thermal disinfection or pour litres of chlorine down them. And they were taking samples before and after. It didn't make any difference. Across 35 wards in the Geneva hospital, they still got contaminated sink traps and sinks. The only thing that did make a difference was removing that U-bend at the bottom and giving the sick a U-bend. Biofilm, it's quite possible that most of the trouble that we have with the sinks is due to biofilm. Biofilm is like a village of all sorts of different people covered up in a protected polysaccharide glue. And it's in the tiniest crevices in all surfaces. That's hard surface biofilm. There's wet surface biofilm in those sink traps. And the organisms are very happy, thank you very much. They talk to each other, and they manipulate their DNA so that if there's a little bit of bleach around, not enough to kill them, they then become tolerant or even frankly resistant to the effects of chlorine and other types of disinfectant that we use. And this is all published now. We know all about this. Very occasionally, an organism will get a bit restless and decide to take off. It'll become planktonic, leave the biofilm, and it's there for people to touch and to take elsewhere. So, in fact, if you scrub a surface with disinfectant as hard as you possibly can, you come back 8 to 12 hours later, you will find pathogens there on the surface again, because you've released planktonic organisms from the biofilm. So, we also know already, and I only just found one paper here, that UV radiation doesn't penetrate biofilms very well. But I'm afraid I don't know what sort of UV radiation is, because you guys are the experts on that. It's not far UV, I know that. So when UVC works, and I just trawled about it a little bit to find some papers in medical type journals, it was not difficult at all to find in vitro studies mainly, but also one or two in vivo studies of what happens when you irradiate surfaces with UVC, or if you clean the air with UVC and then have a look at the bioburden on surfaces. Yes, there is an effect, absolutely. But then when you want to translate that into a natural effect on healthcare acquired infection, then I ran into a stumbling block. All I could find at first were the original experiments from Wells, who used UVC radiation to try and stop the transmission of measles in children's schools. I think this was in New York, this is a long time ago, 1937. The trouble is, none of the latest studies could reproduce that, possibly because of the fact that people can get measles in impunity, and not just in the school. But then, of course, there were the classic Riley experiments where they fed air from a TB ward upstairs to where they've got guinea pigs in cages, and the ducts that were irradiated with UVC, the guinea pigs remained well, and those where it wasn't irradiated, the guinea pigs got TB. Classic studies back from the 1960s which told us that TB was airborne. So I suspect that UVC may well have a real impact on respiratory viruses and other respiratory organisms that go through the air, including TB. It may not have much impact on some of the other organisms that we're so worried about. And then just in press now, there's a paper from the American Journal of Infection Control, tells us that a UVC light cleaning technology, which had photocatalytic honeycomb surrounding a UV light, which I think was 254 nanometers, they said, oh, we put this in for a couple of years, and we measured before and after, and we got a decrease in healthcare-associated infections. But they don't really tell you that this was through the pandemic. There were all sorts of things happening during the pandemic which would have stopped the transmission of organisms. And particularly so, their numbers are very, very small. So one ITU, I think it was 10 critical care acquired infections down to 3 over a period of about a year or something. I'm afraid those numbers are too small, and the jury is well out with that one. And of course, when UVC doesn't work, well, some papers there. The first one is one that I did with a medical student years ago. We had a handheld UV light source, and we went round to the computer keyboards in the hospital, before and after standardised microbiological screening, to see if it had an effect. No effect whatsoever. The firm that gave me all these handheld UVCs were really upset and demanded all their equipment back onto that study. But there's been a couple of others as well. The norovirus one, which is the second one down, that was an in vitro study where I think they looked at different linings, granite and plastic or something, seeded it with active norovirus, and then either used bleach or UVC to decontaminate it, and it didn't work. So the bleach was much better, was far superior to the UVC. Once again, I can't tell you what sort it was. Two very recent papers, in particular, the one at the bottom comes from a Scandinavian country. Scandinavian hospitals is really clean, they're wonderful. CTP did a lot of floor generally, and the Netherlands. But this particular one, they decided to have an intermittent UVC contraction in the bathrooms, and they would do it before and after standardised screen. No effect. That paper hasn't been published yet. So why? Why does UVC not always have the effect we want it to? Well, have a look at this. This is a mattress from a burns unit, and you can see the staining there on the right-hand side. And that's effluent coming from the burn, effluent coming from the burns patient, which has penetrated the mattress. And it sets off an outbreak, and that molecular diagram there, you can see that's where we do pulse-filled jello electrophoresis to see if the organisms are at all related. And there was absolutely no doubt whatsoever that the organisms from the mattress and from the patients were identical from pulse-filled. It's not quite as good as pulse-filled genomic, but it's not bad. So how on earth would you sterilise a mattress if you contaminate it in that way? For me, as an infection control professional, I would say get rid of it. Get rid of it, get a new one. The trouble is we're dealing with the NHS here in the UK and they're bankrupt. Right, reservoirs you would never imagine. I couldn't help but put up some pictures of the reservoirs of pathogens which have managed to get to patients. Every single one of these has set off an outbreak, and I have been involved in the past 40 years of my life in NHS hospitals. We've got medical equipment there with buttons of a cardiac monitor, top left there, as set off an outbreak. Disinfectants and antiseptics are always getting contaminated, so instead of trying to clean up surfaces, you're actually spreading more germs around. That's an absolute classic. And I'm sorry to say for the Americans, but the hospitals in America like using quaternary ammonium compounds. They get contaminated with granulations all the time. It's a real problem. So you can see the visitors, you can see the commode there at the top, you can see the sandwiches and the water, outbreaks with both of those. Even a scrubbing machine, I've just seen a paper about that in the General Hospital infection, was spreading carbon penetrase producing coliforms around, pan-resistant organisms due to a scrubbing machine for the floor. And of course cockroaches. That's the salmonella there. Yes, I was involved in an outbreak. That was a long, long time ago. And that's my favourite. That's Clostridium difficile stuck in the soles of shoes, which the staff are taking around all over the hospital. So the commonest HAIs are endogenous. There is no doubt about it. Here they are. You've got a line site in, Staph aureus, nose, hand, infection, a catheter, a urinary catheter. The organism that causes a catheter-associated urinary tract infection comes from the patient's gut, and that's surgical site infection there. And I was making sure I wasn't going to upset your sensibilities. There's been generally non-medical audience. You've got a nice picture there of a surgical site infection. That's probably another Staph aureus. It could actually be a streptococcus, and that's come from the patient. So my conclusion is that hospital-acquired infections are multifactorial. Most of them are endogenous. You can't deliver UVC to the inside of the patient's gut. Screening, bathing, and antimicrobial prophylaxis reduce the endogenous HAIs, but not all of them. Our usual traditional infection prevention control interventions, yes, we do target the exogenous causes of hospital-acquired infection. Once again, they're not enough. What place does far UVC have in reducing HAI? I think the question is, what place does far UVC light have in reducing viral respiratory tract infections, the next pandemic? That's where as a clinician, that's where I see UVC. Although I also would like to see it being used to sterilise some of my equipment. Okay, cost benefit is paramount. If you want the clinicians to accept your technology, you have to show that the cost of it is going to be less than the cost of the hospital-acquired infections that you are going to prevent. Thank you very much indeed. I've got a few appointments to make, and one of them is Cat Notes, who's not here. Never mind. Thanks for your attention. I don't know if you've got time for